Welcome back, dear student, to the tetrahedron chemistry classes. In the series of the reducing agents, today I am going to discuss another very important reducing agent, and the abbreviation for that reducing agent is the LDPA, right? And the full form of this LDPA is lithium tri-tertiary butoxy aluminium hydride. It's a very good reducing agent, very selective reducing agent, right? And how you can prepare this? You can take lithium aluminium hydride and react that lithium aluminium hydride with this tertiary kind of the tertiary kind of the aldehyde. 3 moles of this will be required, and ether would serve as a solvent here. So you will have this kind of the molecule, and this basically is your LDPA, lithium tri-tertiary butoxy aluminium hydride. As you can see here, only one hydrogen is present here, so we can control the reaction at any time. That means there will be no exclusive that means the reducing nature of this will be very mild due to the presence of this one hydrogen only. This is the first reason. And second reason is that you can see the size of this reagent, this reducing agent, and compare this size of this reducing agent with that of your lithium aluminium hydride, then you will find it is a very bulky in nature, right? So due to its bulkiness, right, and the presence of only one hydrogen, it is a very mild reducing agent. And since it is a very mild reducing reagent, it is very selective. Okay, and this is the general formula for this particular reducing agent, aluminium in the center, and you see this is your tri-tertiary butoxy group. This is one time, and second time this is your tri-tertiary butoxy, right? And this is again your tertiary butoxy, not tri, this is tertiary butoxy. This is also tertiary butoxy, this is also tertiary butoxy, and these are present 3 times, so they are tri-tertiary butoxy. And this hydrogen which I have shown with this white color is basically the hydrogen which we can remove from here as hydride, right? Since it is a hydride donor, so it can act as the nucleophile, as I have written over there. Bulky, very bulky in nature, bulky hydride donor, and hence it can act as a nucleophile, right? But it is always better to say it's a hydride donor, a reducing agent, rather than the nucleophile, because there is a marked difference between the nucleophilicity and the basicity. I hope you know what is the difference between the nucleophilicity and basicity. If you don't know, I am giving you the link in the description box. You can go there and learn about the nucleophilicity and the basicity, and also the link is flashing at the right top corner, you can see there. Okay, and then you can see here it is more selective in nature. More selective means if you have more than one kind of the functional group present in the molecule, then this LDBA will attack only a particular functional group. And what kind of the functional group it can attack, and what functional groups it cannot attack, or it will leave those functional group as such, we will discuss in a little while. Okay, right. So functions, I have written functions here. Functions, the important function of this is the reduction. It is used for the reduction processes, and most famously or generally it is used for the reduction of the acid chlorides, right? And these acid chlorides can be reduced to the aldehydes, right? And this is your LDBA, and THF, tetrahydrofuran or ether, you can take as a solvent, and after the protic workup, your acid chlorides will convert into the aldehyde, right? But instead of taking this LDPA, if you take your lithium aluminium hydride, then the reduction goes on in a pretty long way, and aldehyde get further reduced to the alcohol. So if you want to stop your reaction only up to the aldehyde stage, then you should use a bulky, mildly reacting reducing agent, and this LDBA serves this purpose pretty well. Okay, secondly, if your compound is having the ketones or the aldehydes, then with the help of this LDBA, under same conditions, you can convert the aldehydes and the ketones into the aldehydes. Depending on the nature of the aldehyde and the ketone, your alcohol may be your primary, secondary. Okay, and then similarly, if you take amides, another acid derivatives, So with this, Ltba will convert these amides again into the aldehydes. Similarly, if you have the phenyl ester, so I missed a point here, right, L. If it is a phenyl ester, so these phenyl esters are also converted into the aromatic aldehydes. Similarly, imidoyl chlorides can also be converted into the aldemenes. Aromatic disulfides, it's a very important application. Aromatic disulfides can also be reduced to the thiols with the help of the Ltba, lithium tri-tertiary butoxy aluminium hydride. Okay, this is the full form of this one. And lastly, unsaturated ketones, if you are having, then your unsaturated ketones can be converted into the saturated ketones. That means only double bond will be reduced or triple bond will be reduced, but your ketone will remain intact. So these are the some of the important applications, and we will see few of them how we can do the reaction. Okay, right. So this is my first application, reduction of the acid chlorides, and these acid chlorides can be very easily reduced to the aldehyde by using this Ltba. Of course, your tetrahydrofuran would be there as your solvent, and the reaction actually occurs at very low temperature, that is at minus 80 degrees centigrade, and the reaction is quite simple. You can straightforward write the product, and your product would be your benzaldehyde. Okay, you will not get benzyl alcohol in that case, but you will get your benzaldehyde, right? And simultaneously you will also have the sum of the byproducts in the reaction mixture. One is the lithium chloride, and the remaining part is your aluminium. Again same thing, OCCH3, your tri-tertiary butoxy type of thing. Okay, just like that. So these are the two byproducts, and the mechanism of the reaction is quite simple, and we can write that mechanism as well if you want. Okay, so for this I will write my, like, H is like that, it is connected with the aluminium, of course it is negatively charged, and lithium will also be there as a positively charged species. Okay, and then your oxygen C, and then CH3. Okay, and then it is present at 3 times. Okay, so this is something very, very important. You should note this point, this particular point, right? Very important. Okay, and see, this I made a mistake here. No, not mistake here, this is fine actually. Okay, CH3 is present 3 times. Okay, and what will happen then, this your hydride, because it is a hydride donor, it will attack on the electrophilic carbon, this carbonyl carbon, electrophilic carbon. Okay, and this electron pair will shift over there. Don't forget, 2 lone pairs already are there on the oxygen atom. However, there is no need to write that particular electron pairs over there, over here. That's why I am avoiding okay, to draw that, to draw lone pairs. Okay, and then you see what will have here, what will you have here, this is, you see your benzene ring. Okay, and you see this oxygen is negative, and this is your hydrogen, and this is your Cl, right? And one very important thing is that, which you should know actually, this chloride, due to the little bit bigger size, it is a good leaving group, not a very good leaving group, but it is a good leaving group. There is a difference between the good and very good. Okay, so it's a good leaving group, right? So this species you have produced here, and don't forget to put the negative sign over there, because it has the electron pair has moved over there. Okay, and finally what will happen in the next step, you see I'm drawing it just like that, this will come back, this electron pair will come back, and this oxygen will be knocked out and finally taken up by the lithium as the lithium chloride. So you will have minus LiCl here, and then you will also have aluminium OCCH3 times 3. Okay, and thrice, sorry, it should be 3 here again, like that. Okay, and then you are having your final product, and that final product would be your benzaldehyde. So the reaction mechanism is quite simple for this one, but this is a very, very important bulky reagent. I hope this is quite clear to you. Okay, now moving to the next slide. Now see, this reaction is a little bit more important. You see here, acid functionality is there, which can be reduced. Acid can be reduced to the aldehydes and alcohols, right, as well, like that. And similarly, this is ester. Ester moiety is also here. This ester can also be reduced. But please remember this very important point here. Whenever you have these ester moiety present here, okay, along with this one, your acid moiety, okay, so only your acid part will be reduced with this LDBA, okay, and your ester will remain as such. So it will not affected actually, okay. So first of all, in the first step, we are taking the thionyl chloride here, SoCl2. So when SoCl2 reacts with this one, so what it will form? So just like that, so I'm writing here C double bond O, OCH3. This is your ester part, and please don't get confused. I have written the ester moiety in that manner. Here I have connected with the oxygen here. So a method of writing is different. What you can do, you can write in this particular format here, because it is not getting reduced in this reaction. So I'm not pretty much bother about this functionality, okay. So what will happen in that case? It will form C double bond O Cl. You know, it's a very famous reaction. When you react with the carboxylic acid with the thionyl chloride, you produce your acid halides. So sulfur dioxide will be removed from here, and HCl will also be removed here from here. And since these two are the gases, it's a very important reaction, okay. Now you have produced this chloride here, and then finally what will happen? You will take your LDPA, which is this one, LDPA, and THF you can take, and of course your temperature would be minus 80 degrees centigrade, and then you will have your final product, and that final product would be your C double bond O H. This is your benzaldehyde type of formality, benzaldehyde functional group, and this is your ester part, okay. This is your ester part. So what you are noticing here, when LDBA is reacting with the compound which is having the two functional group acid and ester, it tolerates ester basically, okay. It tolerates ester and don't touch it, right. It will not touch this one, and finally only your acid part will gets converted into the aldehyde parts. It's a very important reaction, okay. Now moving to the next one, this is your a reduction of the ketones. So I have taken this particular example of steroid. Students who are actually learning natural product chemistry or any type of the chemistry, biochemistry, they know the how to write the steroid skeleton. So this is the skeleton for the steroid, and what is the special thing about this molecule is that it is having the ketonic functionality, right. Ketone is there, and along with the ketone, double bond is also present, right, which is in the alicyclic ring, and cyanide nitrile is also there. And if you take your say lithium aluminium hydride instead of LDBA, so what will happen? This will get converted into the alcohol. This will this double will become single bond, and this cyanide will become your amine, right. If you take the lithium aluminium hydride in place of the LTPA, okay. But when you are using LTBA for this particular reaction, only this ketone will be reduced to the alcohol, while this LTBA will not touch your double bond and your cyanide group, okay. So what would be the product in that case? Again, you can draw very simply. So first of all, you can write this thing here. Cyanide is over there, it will not reduce with this LTBA, and this is your ester functionality. This is the 5-membered ring, and this will get converted into the CH, sorry, not CH, C was already there, and then you are having CH3, and it will get converted into the CHOH, right. Of course, you need the protic workup. Why protic workup? Because this LTBA will only provide your this particular hydrogen. So please remember this particular point. This hydrogen is coming from reagent, right. That means LTBA, right. It is coming, this hydrogen is coming from LTBA, and this hydrogen is coming from the protic workup. So instead of writing the solvent, I can write the protic workup. So if you want, then you can write here H positive. Okay, so what you are observing here, your double bond and cyanide remains intact in the molecule while your ketone gets converted into the alcohol. So it's a very important reaction. Okay, now moving to the next one, reduction of the phenyl esters. If you have the phenyl esters again, so in case of the phenyl esters, you see cyanide is also there, phenyl ester is there, right? If you are having the phenyl esters, then this phenyl ester, basically this ester will convert into the aldehyde, right? Earlier one in this particular slide, right? Here you can see this alkyl ester actually is not touched by the Ltba, but if you have, so my next important reaction is the reduction of the phenyl ester. So this is the phenyl ester, okay? And in the earlier case, you can see here when you have the alkyl esters, in this case, so this alkyl ester actually was not reduced by this Ltba, right? But when you have the phenyl esters, right, this is the example of the phenyl ester, okay, that means the ester of the phenol, right? So this can be very easily reduced, right? So how you can reduce this? First of all, you see this cyanide will not get reduced from here, okay, but only your this ester part, right, will be reduced to the aldehyde, okay. So what will be the product? Product will be just like that, OCN and C double bond OH. This is the product. So how the reaction mechanism goes for this one? This is LDBA, this is your hydrogen, okay, and since this LTPA is the hydride donor, so it will attack on the electrophilic carbon. This will get shifted over there, and then you will have this species, and the species would look like this. This is your benzene ring, carbon, and now this carbon will have the hydrogen, of course oxygen, this negatively charged, and this is your OCH3, this part, and here cyanide is attached, okay. And then what you left with, this species, which is your aluminium, okay, and then your OCCH3 times 3 times, okay, and of course your lithium positive is also there. So what will happen in that case? So this will attack onto this one, okay. When this will attack onto this one, what it will form? This is your benzene ring, there is no problem in that, and this is your cyano part, and here you can see carbon, single bond oxygen negative, and I am writing hydrogen here, okay, and then your OCH3, just like that, and this oxygen gets connected with the aluminium OCCH3 3 times whole thrice, okay. This species you are having, and finally what will happen? So this oxygen, this will be donated here, okay, and this will be knocked out, and oxygen this will leave from here actually, okay, and then you are having this species oxygen C double bond OH plus this CH3 OLI, okay, this lithium ion will take this part actually, and then you left with what? AlOCCH3 whole thrice. So this is your possible mechanism. I am not saying that it is the 100% correct mechanism which I have explained here, okay. There may be some error, but this is the most acceptable and most possible reaction mechanism for this reduction of the phenyl ester by Ltba, okay. Now this is my last application of this one, for this Ltba, and this application is the reduction of the aromatic disulfides, okay. So these are the aromatic disulfides, they can be very easily reduced. The condition is what? You can take the two equivalents of Ltba, tetrahydrofuran would be the solvent, and 50 degrees centigrade would be the temperature. A little bit higher temperature is there, 50 degrees centigrade, okay, and protic workup will also required, because without protic workup you cannot form your compound. So how the reaction goes? It's quite simple. See, it is very important to note that the hydride which are present here in this Ltba, it is actually responsible for the breaking of this particular bond. And when this bonds break up, and after the protonation, this sulfur bond will convert into the SH, and you will get the alcohol. Okay, so what would be the product? Product would be this benzene ring, chlorine at this particular position, and this is SH, thiol. Okay, two of this will be required. And the important thing is that this Ltba is a quite heavily selective in nature, so 100% of this product will form, and reaction will occur less than in a minute. Less than a minute. Only under the 1 minute you will get your product. And same thing will happen here again. You see, this bond gets cleaved, the sulfide bond. This will get converted into the SH, two of this one, and cyanide will remain intact. There is no problem in that, right? And again you can see 100% product you will have. This is the beauty of this particular reagent, and you will get this, you will get completed this reaction only in the 2 minutes. So in the 2 minutes you will get your product. And next is, this is your methoxica O para methoxy compound. Okay, and again the same reaction will happen here. This SH, two of this, and OMe, right? But here you can see that reaction will occur at the 25 degrees centigrade, and 4 hours, up to 4 hours. The reaction time would be very high in that case. Okay, and when you take the very bulky, you see ortho and para, at ortho and para position you have the bulky alkyl groups attached here. So due to this bulky nature, the reaction rate is very slow, and this reaction actually occurs in the 24 hours, right? Not 24 hours, I think, say in 3 hours, not 24, in the 3 hours, right? But the important thing is that temperature would be very high, right? So at this particular temperature only the reaction is favorable. If you decrease the temperature up to 25 degrees centigrade, or say up to go to 0 degrees centigrade, then this will not happen. Actually the reaction will not happen very easily. Okay, but again you can see the products are quite simple. This is your SH, and these are your alkyl parts. Okay, so two of such things are required, and again very important, 100% product would be there, while in the earlier case it is somewhere around 93%. So this is the beauty of the Ltba. But the most important function of this Ltba is the reduction of the acid chlorides to the aldehydes. It's a mild reducing agent, selective reducing agent. Sometimes in your examination, say in your CSIR net, GATE, or in the JEE examination, you may have the question from this particular reducing agent as well. Okay, so I hope I made the things little clear to you, right? If you like the lecture, please give thumbs up to my video. And if you are watching video for the first time, please subscribe the Tetrahedron Chemistry classes, and do share with your friends as well. Okay, that's it for today. Thank you very much.